Welcome to Organic Chemistry 2341. Today we're going to be finishing up Module 11, Part 1, Reactions of Alcohols. So as after that, we have our last module, which is Module 11.2, Ethers. So let me go ahead and share my screen and get this ready for everyone to see. And you should be seeing my screen now. So we talked about before other reactions we can do on aldehydes and ketones to make into alcohols. For example, we can react Grignard reagents to addition products. Then we can also use our new reagents, our hydride reagents, the lithium aluminum hydride and the sodium borohydride to create alcohols that way. And by using specific reagents, we can react specific functional groups down to those alcohols. Now we're going to go in the opposite direction. We're going to take the alcohols we have, and we're going to see what kind of oxidizing reagents we can use and what products we'll get. So the first thing we want to look at is the idea of what we call Jones reagents, or they are anything with the chromium oxide in the presence of an acid, specifically sulfuric acid, and a little bit of water. And so what they're going to do for us is they're going to oxidize down our system. So the first thing we need to think about is this chromium has 4 oxygens around it, and it's in its oxidation state of +6, okay? So the first thing we're gonna happen in this acidic condition, we're actually gonna protonate this species here to make our chromium here really electropositive, okay? Now, so that gives us our electrophile. So we're gonna take the electrons from our oxygen here, and that's going to go ahead and act as a nucleophile and create a new chromium oxygen bond. When it does that, it gives us our oxonium cation here, which then it can transfer that hydrogen to one of the hydrogens on the chromic acid, and then that decomposes and liberates water and another equivalent of the hydronium ion plus this chromate ester. Notice we have a chromium oxygen carbon bond. Okay, so the other thing to notice about this system is that there are 2 hydrogens on this carbon here next to the oxygen. That's going to play a critical role on whether or not this oxidizer can oxidize our material to our whatever our products might be. Okay, so let's look at what happens next. The next thing that has to happen is those hydrogens play a critical role in what's going to happen next, because if we take our acid and protonate our carbonyl on that, that carbon chromium oxygen double bond, we have now created a new electrophilic chromium. And in this case, what it's going to do is it's going to take the electrons from that chromium oxygen bond, and then that's going to decompose into our chromic acid here. But when it does that, it also has water coming in as a Lewis base to take away that hydrogen to give us our carbonyl compound. So technically this is an E2 elimination because we have our leaving group leaving and our base deprotonating our hydrogen at the same time. We know this is an E2 reaction because we don't have any rearrangements in this system, so we have an E2 mechanism. Okay, so that's great. We formed an aldehyde here. Unfortunately, the fact is that aldehydes are one of these interesting structures that when we have them in the presence of water, they actually form what we call hydrates. And when we form a hydrate, what that means is we're going to add water across our carbonyl carbon. And when we do that, we end up with a diol, a geminal diol, or 2 alcohols on the same carbon. And so this compound right here then has an alcohol on it. If it has an alcohol on it, it can act as a nucleophile and attack our chromium center here to generate our intermediate, which gives us, once we deprotonate this side here, gives us our intermediate chromate ester. And then just like before, by protonating, grabbing this here or having the base pull off here, we end up going back to our chromium oxide derivative. But notice we've transferred another hydroxide to our carbon. So now instead of having the aldehyde, we now have a carboxylic acid. Okay. So Unfortunately, because of the presence of water in the chromic acid system, where we have chromium uh, oxide 3 plus H2SO4, SO4 plus water, we always have water present and it'll always create that carboxylic acid. Okay, so what if we had a secondary alcohol? If we have a secondary alcohol, the first step would be, of course, to create that chromate ester here. But when we create that chromate ester, what's important here is we only have one hydrogen to transfer, okay? We have one hydrogen that can be pulled off by our base in our E2 mechanism to generate our carbonyl compound plus our chromium center, okay? So that means that secondary alcohols are oxidized down to ketones, and the reaction stops, even in the presence of water, okay? Because the ketones are less likely to form hydrates than the aldehydes. Okay? So that means that, and even if it did form one, there is no additional hydrogen to pull off, okay? We only had one hydrogen, it can only do this oxidation once. So secondary alcohols will always yield ketones from our system. Primary alcohols in the presence of aqueous chromic acid will always yield carboxylic acid. So, well, but hey, wait a minute, the intermediate was an aldehyde. Can't we just stop it at the aldehyde? And well, yes, we can, if we remove water from the equation. So let's go ahead and figure out why we can do that. Oh, no, let's first talk about tertiary alcohols. Okay, so I said before in our primary alcohol, we had two hydrogens to transfer and it ended up becoming a carboxylic acid. In our secondary alcohol, we had one hydrogen to transfer and it became a ketone. What if we have no hydrogens to transfer in the presence of a tertiary alcohol? Well, it turns out that that tertiary alcohol can still act as a nucleophile to form your chromate ester. Unfortunately for them is that there is no hydrogen for the water to act as a base. Therefore, we cannot do an E2 elimination, okay? And the only things we have to leave here are carbon anions, which are very bad leaving groups. So we're never gonna see that happen, okay? So that being said is that we form this chromate ester, but then when we add water to the reaction, instead of oxidizing, we regain our tertiary alcohol. So there's no reaction in tertiary alcohols. So primaries form carboxylic acids under Jones reaction. The secondaries do ketones and the tertiaries do no reaction at all. Okay, so that hydrogen is the very important thing. And in that first primary alcohol, we saw that it had that intermediate where it did form the aldehyde we want with the oxidation, but it didn't stop because it formed that hydrate. So if we change the reaction such that we don't have any water there, we can actually stop it at the aldehyde. Okay. The problem is with Jones reagent, that wouldn't be soluble in a system that is not that does not have water in it. So we trick the system. And we trick the system by turning it into something that is organic soluble. So to trick the system, we start with the same base, which is our chromium oxide here. And we react it with pyridine and hydrochloric acid. What this ends up doing is pyridine acts as a base and creates this pyridinium cation. This pyridinium cation is soluble in lots of organic solvents. Okay. Now, in the process, it generates the chromium oxide with the chlorine on it, okay? So that becomes chlorochromate. So we basically have now a organic soluble oxidizer called pyridinium chlorochromate, or PCC. Most of the time you'll see it as PCC, okay? So just like the other oxidizer, the chromic acid with the water in here, what will happen is it'll form that same chromate ester, but in the present without that water, when it does the E2 leave, it stays as the aldehyde. The aldehyde does not get hydrated and it stops, okay? It's very important though that we use a solvent that is specific to this pyridinium chlorochromate. And the solvent we're going to use here is what we call methylene chloride or dichloromethane, okay? The chlorines do not participate. It is just a very good solvent It is a polar aprotic solvent, and it doesn't absorb water very well, and so it stays very dry. Okay, so the key here is we stop it because of the absence of water. Okay, but we couldn't use just the regular reagent because it wouldn't dissolve in a non-aqueous solvent. Okay, so we can now, with the use of the chromic acid or the PCC, we can make primary alcohols into carboxylic acids or aldehydes by choosing our reagent correctly. We can make secondary alcohols into ketones, and tertiary alcohols don't react under either of these conditions. Now, no, you can actually make a ketone with PCC, but it's easier to do it with the chromic acid. It's, well, typically cheaper to do it with chromic acid, but you can use either reagent. All right, so now let's find another way to make alcohols, but in this one, what we're gonna do is we're gonna open up a ring to give us our alcohols. And we're gonna open up a very specific ring, okay? In this case, we're gonna use what we call oxiranes, or they're more commonly known in industry as ethers. I'm sorry, epoxies, okay? So this specific oxirane is a 3-membered ring with oxygen in it. And the whole key to this 3-membered ring, ethers are usually very stable to reactions with nucleophiles or bases, okay? But in this case, because we have our ring strength, these are all sp3 hybridized orbitals. They want to be 109.5, but we're making them be at 60 degrees, okay? It has everything to do with this ring strain that makes it want to spring open and react with our nucleophiles. So they do so in an SN2 type fashion. So we have our nucleophile come in. It has the electrons here. It'll come in and hit the one of the 2 carbons here. The electrons that we're making the sigma bond go up onto the oxygen, giving us our alkoxide ion. And then when we finish the reaction with acid, we end up with whatever our nucleophile was on one of the carbons and our alcohol on the other carbon, okay? Now, there is some specificity to that, and we'll go in a minute. But I want to talk about why just that ring strain changes the activation energy, okay? So if we had a regular ether right here, and we tried to hit it with a nucleophile, first and foremost, it has a huge activation energy to get up here because ethers are very stable and have very low potential energy, okay? The other thing that I want you to notice here is that if we did this, alkoxide would be a leaving group, okay? In this case, it's a really bad leaving group in a linear system, and so the net of the reaction is actually, that is higher in energy than we started with. Therefore, it's endothermic reaction. So not only do we have to add all this energy just to get to the transition state, but the product is less stable in the end. So it's a very unfavorable reaction, okay? However, because of ring strain, we now have our ether, instead of being at this low energy potential, is very high. And it's all about the ring strain. That's why that potential energy is so high, which means we have a much lower barrier to get to that transition state, and the product is more stable than the starting material, okay? So it's an exothermic reaction. So the reaction is favored to go in the system. So when we think about those small rings like that, we look at them being much more reactive because of ring strain. And that when we release that strain, we get a more stable molecule. Okay. So what kind of nucleophiles can we hit it with? Well, it turns out we can do it almost any nucleophile. We can do anything, all the way down to, alkoxides or other things, and they all form different things. For example, if we use hydroxide as our nucleophile, we make a 1,2-diol, okay? The nucleophile is on one carbon and the alcohol is on the other carbon, okay? Now, if we change that to a alkoxide, then we have, again, another good nucleophile, but we form an ether on one carbon and an alcohol on the other carbon. We can do that same thing with a good nucleophile sulfur. We get a thioether and an alcohol. We can even hit it with a Grignard reagent. Ethers are usually very stable to Grignard reagents. We do Grignard reactions in diethyl ether. They normally don't react, but because of that ring strain, the Grignard is a good nucleophile, and we'll open it up. So we create a new carbon-carbon bond on on one of the carbons and the alcohol on the other. Okay. And remember, we just learned about this new nucleophile, the hydride. We can do that exact same thing with that new nucleophile, the hydride, the hydrogen -1, and we get a hydrogen on one side and the OH on the other. And again, any good nucleophile will open this ring, creating another opportunity for us to create a carbon-carbon bond, just like we did up here. Notice we have carbon-oxygen bonds, carbon-sulfur bond, carbon-hydrogen bond, and these two give carbon-carbon bonds. So that means those two that give carbon-carbon bonds give us an opportunity to create bigger and bigger molecules. Okay, so is there a difference in the regiochemistry of it based on what kind of conditions we have? And the idea would be that you would think, just in general, under neutral or basic conditions, you would have the reaction take place just by sterics, right? When we talked about our normal SN1, SN2 type reactions, sterics was a dominating factor, right? So in the case of this first one under basic conditions here, meaning that we don't have any acid, meaning that we have a nucleophile that's probably already deprotonated, okay? When we have that condition, the nucleophile is going to go to the least sterically hindered carbon, the least substituted carbon, and undergo an SN2 type reaction. So our SN2 type reaction is looking for that least substituted carbon. And what that gives us is our alcohol is on our now more substituted carbon. Okay, so that seemed pretty straightforward. But it changes around when we do it under acidic condition. And it has everything to do with the idea that we've changed the polarization in the bonding around that epoxide. So let's look at that. So in the case of acidic conditions, instead of just having our neutral nucleophile come around here and attack it, because we can't have an anion because we have acidic conditions, right? We can't have like an alkoxide or something like that as our nucleophile. We have to use a different type of nucleophile. And since we have acid, the first thing we're going to do is protonate the oxygen and give us the oxonium cation right here. Okay. When we do that, that makes that bond elongate because we have a positive charge on oxygen here, and that is elongating because we don't have the full value of those 2 electrons in that sigma bond, and therefore we get a polarized bond. And in this case, when we polarize the bond, we end up forming a partially positive carbon on one of those sides. Now, we could form it on this side or this side, okay? But we now have to think about carbocation stability. Which carbon is going to more likely stabilize that partially positive charge? And we know that carbocations, or tertiary carbocations in particular, are the most stable, meaning that this bond is going to elongate, giving us the most substituted carbon, and that most substituted carbon is going to have a partial positive charge. Now, it can wait around for even a weak nucleophile like water, or neutral alcohol, or a halogen to go ahead and do the reaction, okay? Because we've already formed that partially positive charge, weak nucleophiles can come in and open that reaction, giving us the opposite procedure where we have the alcohol on the lower substituted side and our nucleophile on the higher substituted side, okay? So we can control the regioselectivity. We can select which side we want the alcohol to end on. We can choose which side we want the nucleophile to end on, okay? And it's all about whether or not we're polarizing our bond or we're using sterics to control our thing. So in this case here, we're using electronics. In the case of the acid conditions, we're using electronics as our major component that's telling us where it's going to go. In the base catalytes with no protons in it, we're using our sterics as our major issue here. Okay. So with no protonated epoxy, sterics dominate. With a protonated epoxy, stability of that partial carbocation dominate. Okay, so what does that look like? Oops, it's down here somewhere. All right. So if that's true, then we can actually use that to our advantage to make a bunch of different things. Okay. So in the case of looking at it in a different way, we can actually create new functional groups where we can get a difunctional material as a diol, or reacting with a very poor nucleophile like alkoxide, like an alcohol, we can actually get to that ether as well. So before, in those basic conditions, we were actually attacking with hydroxide or an alkoxide here. We can actually end up with the same product under those acidic conditions. Okay. Now, in the system where we have a symmetrical system, so there's one's not favored over the other, we're just going to end up with a 1,2 diol or a 1,2 alcohol ether. Okay. So this is actually kind of good if you also have something else on the substrate that you don't want a strong nucleophile like hydroxide or the alkoxide to come in and react with. Or let's say you didn't want to have an elimination reaction, side product reaction. This is a good way to control it because you're forming that partial positive charge and letting a weak nucleophile come in and do the work. Now we can also use that to our advantage to change the reaction up a little bit, because if we did it in acidic like HCl or HBr, we can actually do the halohydrogen reaction, which means we're going to take our epoxy right here, and we're going to add hydrogen to the OH, and then on one of the two carbons, we're going to end up adding a halogen. So we have a hydrogen or an alcohol and a halogen on the 1,2 positions. And those are very useful synthetically to build long chains. Okay. So the great thing about this is that all you need is some aqueous acid. It'll protonate your epoxy first, and then whichever counterbalancing halide here, it'll come in as a nucleophile and bring open the reaction, giving us our products.